This short presentation outlines how you actually do a t-test to test for significance. We've previously discussed what significance and probability mean. This is one of the ways that you can come up with a p-value for comparing your data. The student t-test is based on the normal distribution, and you've heard quite a lot about the normal distribution and its properties, and by exploiting this the t-test can take some shortcuts and therefore be more powerful. The first thing when doing a t-test that you have to decide is whether to do a one or a two-tailed t-test. Now, a one-tailed t-test is asking a question such as, is population A bigger or smaller than population B? So there's a directionality to it. And a two-tailed test is asking, is the mean of A different from the mean of population B? So the second of those, the two-tailed test, is, if you like, more general and less specific. While a one-tailed test is more powerful, a two-tailed test is more usual, and it would be unusual for you to use a one-tailed t-test. And you must think carefully about why you're using it if you decide you are. If you had set the p-value to be, a significant p-value to be 0.05, in a one-tailed test, remember you're comparing whether something is bigger or smaller than another sample, then your 5% is all at one end of the normal distribution, because you're only interested in the difference in one direction. However, in a two-tailed test, you're looking at 2.5%, the 5% being split to 2.5% at either end of the range, because you're just interested now in whether the mean of this distribution is different from the mean of another distribution. Here's some examples of the other thing that you'll have to deal with when choosing a t-test is whether you're using paired or unpaired data. And these two examples illustrate that in the context of, say, medical research. So if you had a blood pressure lowering drug that you wanted to see if it worked, you might take a group of subjects and you would measure something about them, say their blood pressure, before you gave them the drug, and then you would measure the same person for their blood pressure after you'd given them the drug. So the same subjects are tested in both cases. So the two results are paired because you know both results are from the same person. Obviously in this case you remove some of the variation in the system because in a sense each person is their internal control. More normally you would use an unpaired t-test, and in this example, say you had 100 subjects that you were going to test the efficacy of a drug on. You might randomly assign 50 to the treatment and 50 to the control, and so there's no relationship between any individual who's taking the drug and any individual who's taking the control or a placebo. So an unpaired test is potentially more normal. Okay, so here's a hand-worked example of a t-test that illustrates some of the points. I don't necessarily expect you to know the detail, and in most situations you will almost never do this, but it does allow us to show some of the assumptions that are made and think about where the numbers that you get out of computer programs when you plug them into spreadsheets, where these numbers actually come from. So I think it does give you a better understanding of the process, and therefore more power in when you interpret these data on your own results. So let's say we have a test where we're looking at the effect of light or dark on the germination of seeds, and we've sown seeds in a petri dish, 30 seeds, and we record the number germinating after 2 weeks in both light and dark. And in this case we've got 3 replicates in the light and 4 replicates in the dark. So in the light, one petri dish, there were 10 germinated, 5 germinated in another, and a full 30 in a different one, and these are the numbers that germinated in the 4 petri dishes that we used in the dark. One of the things obviously that this shows, this will be an unpaired t-test, is that you don't have to have equal sample sizes in both treatments. A word of caution though, we're saying we're going to use the normal distribution, the t-test which uses the normal distribution to take some shortcuts and therefore give it more power. We're doing this to with only a small number of samples to illustrate the process when calculating by hand, just to make it easier. But this word of caution is that if you need to be able to demonstrate that your data is normal in order to justify using a statistical test that is based on normality and thus exploits its power. If you look at these points here, if we've only got 3 points, such as we have in the light treatment, sure enough we can fit a normal distribution through them. But honestly, how confident are you in that is the normal distribution that fits these points, or that these points are normally distributed? For example, we could fit a completely different normal distribution through them, or an even radically different one, which are all equally good fits of a normal distribution to those points. We could also fit a non-normally distributed line through those points. So we have no confidence, in fact, that small numbers of samples are normally distributed, and so we would not routinely or commonly use this type of test, this type of normality-based test, on a small number of samples, because we can't tell if the data is normally distributed. So if we've got more samples, we've got a much better chance, as you can see on the right hand side here, in being confident, either by observation or by actually doing a test that tells us for a fact that it is normally distributed, that the data is normal, and therefore we can exploit the power of the shortcuts that are provided. So that's just a word of caution when doing your own tests. Don't do t-tests on small numbers of data points. Okay, so given that we're cheating in this case, just so we can use it for demonstration, what's the first thing we do? Well, as you may already know from previous stuff we've presented to you, the first thing you do is establish a null hypothesis. And in the present case, the null hypothesis would be that the light-dark treatments have no effect on the germination of these seeds. The second thing we do is calculate the mean numbers of seeds that germinate in both the light and the dark. And this is the equation, the total numbers divided by the number of observations. And for the light, it's 10 plus 5 plus 30 divided by 3, which is 15. And for dark, the mean germination rate is 20. And for each of these is the number in an individual Petri dish. The next thing we do is calculate the differences between the means, and that's obviously very simple. The difference between the means is 20 minus 15, which is 5. Now we need to get some idea of the variability in the system, and so the next thing to do is to calculate the variances of the individual means. And this is done by summing the squares of the data, and then squaring the sum divided by the total number of observations. Again, I wouldn't expect you to remember these things. It's the principle that you're calculating the variance and getting some idea of the individual variance. So that sum there, if you can see what we've done, if you look at that equation at the top and see where those numbers come from, which ends up as being 1025 minus 675, which gives us the variances there of 350, and in the case of the dark grown plants, it's 150. Remembering to divide by the different numbers of observations in our samples, 3 in the case of light and 4 in the case of dark. Now we take that and we calculate an estimated variance of the two samples taken together. And this is actually another assumption that you make, and you will have to choose this option or not when you select online or Excel-based t-tests. You're assuming, in order to do this, that the variances between the two samples are equal. Okay, and that's an assumption we make. Again, you can test for it, but in most cases people don't. We just assume that the variances are equal. Again, it provides a more powerful test. So to do that, we take the figures from the previous calculation and we divide by the number of observations minus 1, for reasons I'll come back to in a minute, which gives us the pooled variance of these two samples being 100. It's a number we're going to use again in a minute. We then go back and calculate the variance of each mean from that pooled value. And then in that case, it's the variance of the mean is the figure we've just calculated, same in both cases, divided by the number of observations. So for the case of the light plants, it's 100 divided by 3, or 33.3, and for the dark plants, it's 100 divided by 4, which is 25. Now we come to the important bit, the bit that's most useful. We now calculate the t-value, and this is something which will directly give us the p-value. We're going to look it up in a table. So this is the sum, so it's the difference between the means divided by the two parameters we calculated in the previous slide, added together, and then the square root of those. So in this case it would be 33 plus 25, take the square root of that and divide that into 5, which gives us the final t-value of 0.655, and this is the figure we're going to look up in a table of significance values. However, we've got to do one more thing before we do that. We've got to decide on how many degrees of freedom we've got, because that will tell us which row of the table we look in. The degrees of freedom for any experiment can be defined as the number of parameters of the experiment that can vary independently. So let's think about what that actually means. If we think of this sum here, 1 plus 2 plus 3 plus x equals 10, the numbers, we've got 4 numbers there, but only 3 degrees of freedom, because by the time we get to x, we can calculate what x is, because it's invariant. It can't vary now, because it has to in fact be 4. There's nothing else it can be, so it's not allowed to vary. So the degrees of freedom is usually the number of observations, in this case 4 minus 1, because the last one, once you get to the very last one, it can't vary. Now for the experiment you've just done, you've got 3 replicates in the light and 4 in the dark, and so the total degrees of freedom is the degrees of freedom for each set of observations minus 1, for the reason explained above, added together. So the degrees of freedom is 3 minus 1 for the light grown plants and 4 minus 1 for the dark grown seeds, so that is 2 plus 3, which gives us 5 degrees of freedom. So we've now got 2 numbers. We've got the t-value and we've got the degrees of freedom. We then convert this into a p-value. So we simply look this up in a t-table. There are loads of t-tables available. You can find them online, you can buy books of them. They're all the same, they're already been calculated. So you can see what we have across the top is a list of p-values, and then we have columns of these t-values. Now our degrees of freedom, shown here in the column on the left, is 5, so we need to look along the row where there's 5 degrees of freedom, and we need to find our t-value, which is 0.655 here. So it's clearly, you can see as you go to the left, these numbers get lower, and in fact our t-value is certainly less than 0.05, because it's well less than 2.57, and it's actually less than 0.1. It's certainly 2.02 is the cutoff point for 5 degrees of freedom for a t-value for a significance of 0.1. So our p-value is not only less than is greater than 0.05. Our t-value, our p-value, sorry, is actually greater than 0.01. So we've now got a range of p-values, of significant values, that we've read off this table. So you go along the degrees of freedom, find where your number is, and then look up, and that tells you what the degrees of, what the probability, what the significance value of your test is. And this is the value that you then interpret in terms of the significance of your results, as we've discussed in previous presentations. So that's the important bit now, is to interpret the results, because that's where the biology is. So you found a p-value which is greater than 10%, greater than p is 0.1. So that tells you, or you should know, that if that experiment was repeated 100 times, then on more than 10% of the occasions, so greater than 1 in 10 chance, we would accept the null hypothesis. So we have to then conclude that we accept the null hypothesis, and then that we conclude therefore there is no difference in germination rate in the light and in the dark. Now I emphasize that I merely showed you that to show you some of the components of where these probability values come from. In most of the things you do, you will do these in a maybe in an Excel spreadsheet or using R to calculate a p-value directly. But the things that I want to take away from this are the assumptions that you have to make when doing a t-test. So you have to be cautious about normality and sample size and things like that. And you also have to be careful in your interpretation of the result and what it actually means biologically.